All right, today we'll be discussing concept of stress. Stress actually is a very interesting term. So if I take help of Google to understand what is stress, and just let me open Google and see what we get. Okay, let us find stress. And then you will see, okay, this is a very interesting picture. And within 0.66 seconds, we get a lot of uh, counts in the search. And firstly, what we get is the mental stress. So, stress is a feeling of emotional or physical tension. So, that's what we get in first impression if we hear this term stress. But in this class or lecture, I am not discussing the mental stress, that stress the human being actually encounter when they face some stimulus or something. So what we are referring is the stress which a material body that like that experience, a material body experience when it is subjected to an external uh, forcing. So if a body is subjected to some external force, then it actually undergoes some deformation. And as a result of this deformation, the material uh, within the body and its neighboring material have some kind of interactions. And the consequences of this interaction is the stress. And probably because you are in second year undergraduate, so you might have encountered this term stress in your first year mechanics. But here we'll get some more insight into the concept of stress, mostly in three-dimension sense. So here we will, what is the difference of what we have already learned and what we are going to learn here is this. So we'll be getting the concept of traction vector and the stress tensor. So stress will be discussed in the sense of a tensor. And then we'll see how we can get the concept of maximum stresses within the body, because we know that the material failure will be mostly due to the stress reaching some limit. So you should know what is the limit of the stress, thereby the maximum or the extremal values of the stresses is important. And then we also will learn the concept of equilibrium, and then we'll move to some other related topic, like how we can understand the which part of stress actually is responsible for volume change of the material and which part of the stress tensor is responsible for the uh, shearing part, not the volume change. So the further details of the stress uh, concept will be discussed. So before going to this traction vector, or sometimes it is also called stress vector, I want to bring those old pictures of what we have uh, in our mind when we hear this term stress. So because we are uh, in the second year undergrad, so probably we have already heard these terms. Okay, so let us see this picture. So in this picture, there are three type of stresses mentioned. So you can see if there is a tensional kind of stress and compressional stress and shear stress. And I think I should not discuss uh, these terms again because we have a clear picture of this stress components like or the terminology. So tension means it is trying to pull the material apart, and compressional means there is something which is the force components are normal to the surface, and it is kind of trying to squeeze the material. And the shear stress is something which is kind of trying to shear off the one material from another. So there is a tangential force component acting on some surface. And then if I pull out this picture, okay, so before that, let me pull this. So if I just consider the normal stress, sorry, this picture is not good. Okay, let us bring this. So this is a 2D picture. We have already seen this kind of picture earlier. So there is a bar, you can say, and it is subjected to two external forces acting in the two ends opposite to each other. So that means they're balanced. So this body is in equilibrium, but if we see some cross section inside, like mm and nn, and that cross section uh, will have some distributed forces. And this distribution, in practical sense, if the length of this bar is not very high or it's not very long, then probably we'll see that they are not uniform. So the middle, because the force is acting at a point here, so definitely in the middle there will be some higher forces acting, and at the end there will be lesser force. So that means the distribution of forces in a cross section may not be uniform. But what we have learned so far that if we assume that these forces are uniform, then we can get a picture which is shown in the third uh, picture here, where uh, the force components are uh, assume uniform, and then we can get a uh, estimate of the average stress as the force F by the area of the cross section A. So sigma average is P by A. But we know that this is a kind of an average sense, but it is not the true picture of what the stress actual actually it is experienced by this cross section, because definitely the middle one will be middle point of the cross section is experiencing more stress compared to the extreme ends. And if we go close to the force, we can see uh, at the ends there will be like this point where the load is acting will have definitely very much stress concentrated near to this point, but far to that point it will have very less load. So that means what we learn here, that stress depends on the point where we are calculating this or trying to find out the stress. So it's a function of space or position. And we have also seen that, okay, let me pull this picture. If we take some arbitrary cross section, not it is like perpendicular to the application of force. So if we take oblique cross section, then we have seen that there are stresses which is acting normal and also along the plane of the cross section, which is the shear stress. So that means the stress also depend on the plane where we are calculating the stress values. So it is both function of point and the plane where we are trying to calculate these stress components. So with this little introduction, let me go back to my PDF and see how we can define a traction vector. So the concept of this tensorial approach of stress was first announced by Cauchy in 1822 as his famous stress principle. So that's why we have a lot of like sometimes we call the Cauchy stress. The tensorial stress is called also as Cauchy stress. So credit goes to the scientist as early as in 1822. Now let us bring this picture and try to understand what we mean by a traction vector. So let us say this is a three-dimensional body subjected to external loads as like P1, P2, P3, it can be up to Pn, and these are point loads. There can be surface loads or pressure, and also movements, body force, etc. And then if we try to cut a section through this body, uh, which is shown on the right side of the picture, and then we try to concentrate on a point. Let us say this point is near to the middle of this, and around that point, if I take a very small area, infinitesimal area delta A, then we can assume that the internal forces acting on that particular area is uniform. So because the area is small, so within that area we can assume that the internal force is uniform. So but this can change as we move along the cross section, different points. If we take different points on the cross section, it may not be same, but uh, at the point of interest, if I take a very small area, within that area we can think of that this is the forces average, the force distribution can be uniform, and then the resultant of that force is shown as delta F. And then this surface also can be defined as with respect to the normal component as n. Let us say that surface has a normal n, and then the traction vector on that surface, which is defined by n, at that particular position of x, is defined as limit delta A tends to 0, delta F by delta A. Now you can see here delta is, though area is is a vector, but here we are taking only the magnitude of the small area A, uh, because that area is defined with respect to the normal component n. So the area can be a vector with delta A times the n hat, the normal vector. So here we are not taking the vector A area, it is the magnitude of the small area A, and it is the force is a vector delta F. So this limit, what we have defined, is a vector, because some vector divided by a scalar component remains a vector, and it actually direction also will be along the same vector delta F. So this vector is defined as the traction vector. So traction vector t, which can be a function of uh, the position x and the normal vector n. So when the position x changes, the traction vector changes, and when within the same position x, when the normal component of the area vector changes, then also the traction vector changes. It is both function of the position and the area normal vector n hat. So you can see the traction vector is a function of where we are trying to calculate it, at which position, and at that particular position on which plane we are trying to calculate it. So that's very interesting. And then on top of that, if we try to calculate the traction vector for a dynamic problem, then we will have the time also as a dependent variable. So it will both depend on x, n, and t. So now this traction vector is sometimes also called as trace vector. And as per Newton's third law, uh, if we take the opposite surface or the adjacent surface of this cross section, what we have taken, we will see that that will have at that particular and the same point, if we take on that other surface, then we will see that the normal vector will be minus n. So that area will have normal vector which is opposite to the normal vector of the previous area. So the position will change, and because of Newton action and reaction, you can see that the force will be exactly opposite. So that means the traction vector on that particular plane, which is defined by minus n, will be exactly minus of t. So t x n will be equal to minus t x minus n due to the Newton's third law, action and reaction. So with the definition of the traction vector, now we are moving to define what is a stress tensor. So you can see that the traction vector actually dependent on the position of the point where we are calculating the traction vector and the unit normal. Now we can see that there are actually two vectors. One is the traction vector and another is normal vector. And here comes the stress tension which relates these two. So uh, the stress tension is defined in this way. There is a Cauchy stress tensor which maps the normal to a surface to the traction vector answer on that surface. So if the stress tensor acts on a particular which is defined at a particular point, acts on the normal vector on a surface, then it gives us the traction vector on that particular surface at that particular point. So T is sigma n hat. So where T is the traction vector, sigma is a tensor, which is a function of the space, and then n hat is the normal vector on a surface. So the equivalent matrix from this equation, we have already uh, done that, how we can represent a tensorial form of equation to an equivalent matrix form. So it is just T equal to sigma n, where T is a column vector, sigma is a 3 by 3 matrix, and n is also a matrix, column matrix of 3 cross 1. So we are dealing with second order tensor, so this is how it is related in matrix form. So we now can conclude that that the traction vector on a plane passing through a given special point x depend on the unit vector on that plane. So because this particular point x will give you a particular stress tensor, so the traction vector then will be a function of only n. If the position is fixed, then the sigma is fixed. All right, so now let us see how we can find the component of this stress tensor which we have defined just now. So now let us say we are using a Cartesian coordinate system, orthogonal set of basis vector e1, e2, and e3, and then the traction vector on that on the plane which is defined by these basis vectors. So basis vector e1 will be normal to some surface or plane. So on that particular surface there will be some traction vector, and that traction vector will call as TEI, which will be equal to sigma EI. So if we take E1, then it is TE1, which is sigma E1, and sigma will be 3 by 3 some tensor represented a matrix for sigma 1 1 sigma 1 2 sigma 1 3, and E1 is denoted by 1 0 0. So then we'll see that we can get sigma 1 1 sigma 1 2 and sigma 3 in a vector form that is written as this: sigma 1 1 E1 plus sigma 2 1 E2 plus sigma 3 1 E3. So similarly for other two basis vectors, we can also get these traction vectors, which will have three components in these three directions. So and also if we take the minus E1, which will be denoted as minus 1 0 0, so then we will see that T minus E1 will be equal to minus sigma 1 1 E1 minus sigma 2 1 E2 and minus sigma 2 3 E3. Now if we try to represent this, so let us see this figure 8 now, which is shown here. So this is my E1 plane. So here we can see I have the first component as sigma 1 1, and second component is sigma 2 1, which is along E2, and third component is sigma 3 1, which is along this E3. So this three components is coming due to this traction vector TU1. So this traction vector will, if we decompose into the three Cartesian coordinate system, we will get these components. Whereas if I take a different plane which is defined, so remember this is actually not a cube. With these surfaces are actually the indication of the planes by separating them with a particular distance, but they are actually defining these components at a particular point. So these planes are just separated to uh, give a kind of pictorial representation. So if I take TE2, the traction vector on the E2 plane, so E2 plane means the plane whose normal is E2, and then we'll see we'll have three components as sigma 1 2 in one direction, and then sigma 2 2 in two direction, and sigma 3 2 in three direction. Similarly for TE3, and also if we take the minus E1, that represents, this is the front and the back side of this x-axis or x1 axis, that will have all this negative of these values, so which is shown here. So we'll have all negative components. That means all opposite directions will get, so these components will be exactly opposite to this plus E1 direction. So that also can be shown, but it will make this picture very clumsy, so that's why it is not shown here. So this is this here you can see these are the 6 components we get due to the stress tensor sigma, and these 3 components actually representing the 6 components. Sorry, there are 9 components, not 6. 9 components are representing uh, the component of traction vector on the 3 uh, unit vector E1, or the basis vector E1, E2, and E3. And now, okay, so we what we see here, we now see, okay, let me bring this sign convention part here. So as per whatever notation we have taken, so you can see the second index. So here you can see this is my one plane, so that one is associated to the second index of this component here in the one face. So it is 1 1 3 1 and 2 1. What is the first index? First index is the reference to the plane, so that is my one plane, and the second index, the direction of the component 1 2 and 3. Okay, so first index is, sorry, the first index is the direction, and the second index is the plane. Similarly, if we take the plane 2, so you can see the first index is the direction of the basis, the direction of this traction vector components in this three basis vector direction 1 2 3, and the second index is associated with the plane 2. But this notation is actually used in continuum mechanics books written by some physicists. If we see tensor concept of tensor or tensor algebra written by some scientists, they use this notation, and that has some advantages of representation of the matrix form, etc. But in engineering, we actually have a little different notation. Actually, it is the opposite of this one. And why that actually doesn't make any difference in the discussion we are having here, because we'll slowly see that whatever we are discussing in stress tensor and strain tensor, these tensor are actually symmetric. So if and we'll prove why the stress tensor will become symmetric and all. So let us consider that this stress tensor is symmetric. That means sigma is a equal to sigma ji, and then the following sign convention can also be considered, because this 1 2 and 2 1 can be uh, interchanged. So that means if I bring here to this two, if I compare, then in the front face sigma 1 1 is 1 1, then sigma 2 1 can be interchanged to 1 2, and sigma 3 1 can be interchanged to sigma 1 3. So that means if I take a sign convention of this component as the first index referred to the plane and the second index referred to the direction, that also become acceptable to us, because the stress tensor is symmetric. So as long as the stress tensor is symmetric, so we can very well consider this sign convention, that the first index, which is referring to the plane, the second index referring to the component of the traction vector in the direction of the three basis vector 1 2 3. So even sometimes we instead of taking 1 2 3, we can use x y z, and then it can be shown as sigma xx, then sigma xy, and sigma xz. So you can see the first x is the x plane, and the second index x y z are the direction along which these components are acting. So this sign convention is mostly used by engineers, and we can also very well use this sign convention, because as I told, we are dealing with a symmetric stress tensor. That means a the sigma transpose and sigma, they're equal. So that's that way it doesn't make any difference. All right, so I'll stop here, and maybe in next video lecture we'll prove this thing, how the stress tensor will become symmetric.